Hello and welcome to our discussion of Chapter E, Essentials. Now this chapter is optional to review. If you've taken the class before, you might want to refresh a little bit on sig figs or SI units. If you've never taken this class before, you'll see this video is in your lab session for day one. So you can view it here, or you can also view it in the lab. Wherever you are joining me, welcome. The first thing that we want to start off with in our discussion of essential information for chemistry is qualitative versus quantitative. We talk about these a little bit in lecture. We're just going to briefly describe them again. A qualitative observation is one that is descriptive in nature. Changes in color, changes in physical state, solid, liquid, gas, those types of things. We can say a little bit about temperature as a qualitative. It's hot or it's cold. Temperature can be either qualitative or it can also be quantitative. It's 78 degrees Fahrenheit today. So qualitative, hot and cold, quantitative, an actual number associated with that observation. Now, so for quantitative observations, they are measurements, numerical values obtained by instrumentation or glassware, so measuring length, volume, mass. With these vary with precision and accuracy. So we'll talk a little bit about those definitions in this video, but they are counted values. An example, number of cats per household in the United States. The nature of the measurement, qualitative or quantitative, dictates the type of statistics can be used during the data analysis. So if we have qualitative data, we can develop some sort of an idea of repetitive observations, and we can find some coding within our qualitative analysis. Quantitative, we can do more math with. We can take averages, we can find medians or modes, most frequent values, things like that. What are measurements? Measurements are very important for chemistry, specifically quantitative measurements. Now, when we get into a scalar or a dimensional unit, we have at our disposal what we call the SI units, the International System of Units. Now, the SI units were developed a long, long time ago, originally developed in, 1875 by 17 countries. On May 20th in 1875 in Paris, the International Treaty of the Meter was signed. The US was part of that. And so we celebrate World Metrology Day on May 20th. And so when we developed these units, the SI unit is made up of 7 base units that defined up to 22 derived units with special names and symbols. So here we'll see a list in a second of our 7 base units, but here's where we all already started as a scientific community around the world to develop a way of communicating with each other in chemistry and in science. Now in November of 2018, just almost a year and a half, 2 years ago, the world measurement experts, yes, there are experts on measurement, they voted and unanimously approved the revision of the SI units that were established to be specifically based on physical constants of nature. We'll talk a little bit about the fun facts of how SI units were developed. Fun history again. What you would need to know are what are the SI units, and that's it. But on World Metrology Day last year in 2019, those changes became effective. Now, when we think about a number, what we want to be able to think about, or a measurement, is not only the number itself, but the actual scalar or dimensional unit. There are 2 parts to a measurement, and those 2 parts are the actual unit and the number. Anytime we are doing some sort of calculation in the lab, we will always have a unit derived with that numeric value. Very rare occasions do we ever see only the number itself. There are some unitless values, and we'll get to them when we get there, but most often we have a unit associated with a measurement. If we didn't, if you said, oh, in the lab I got 172, well, what? 172 what? Bunnies or atoms or grams or donuts? So be specific, right? In quantitative measurements, we can have errors. There are systematic errors or determinant errors, and there are random and intermittent errors, indeterminate errors. So when we're looking at different sources of errors, we're going to talk about these more in the lab for lecture. We don't really look into errors as much, but quantitative measurements do have errors. Here are 7 SI units. For length, the SI unit is the meter. For mass, it's the kilogram. Time is seconds. And temperature, Kelvin. We will dive into the amount of substance is the mole. There's Avogadro's number, which we'll talk about in lecture. We don't often look at the last two, an electric current, an ampere, or a luminous intensity, a candela. We don't really do those in general chemistry. You might see those more in physics, but we will deal with the first 5. And the first 5 are what I really do want you to know. Put a big star by those. You'll get used to those and see them a lot. Now, this is not to say that we use these all the time, but we will use some sort of derivative of these SI units in chemistry based off of what we actually are dealing with. So if we're dealing with the subatomic realm, we might not use the kilogram, we might use the nanogram, right? We'll see some other types of units, and we'll be able to talk about the prefix multipliers within those. Now, just some fun facts. In 2018, why the experts in measurements decided to change the definitions of some of our SI units. Primarily, one of the fun facts, you can read about these if you type in SI units. You can read all about them and how they were developed on the NIST.gov website. And the SI unit for mass was originally developed not with a physical constant. It was actually developed originally called the Lagrange K. My husband would like to tell you the story because he's a big physics nerd.
Okay, I'm such a nerd. Okay. So like all these units, right, used to be measured to like something that you could like observe. So like back in the day, it was like, the meter was like the length of the king's arm and some bogus stuff like that, right? And so up until just recently, all of those had been replaced with like measurable constants in nature, right? Except for mass. And so in this crazy, wacky vault down in the catacombs of Paris, right? There are these crazy SI people. I imagine them in like monks' robes and stuff, like walking around. And what they do is they had this one piece of, Lauren, what is it?
It's a platinum iridium alloy.
Platinum iridium, thank you. Right, and so it's this hunk of metal, right? And they would come, and it was Lagrange K, right? Because they're all French, and so it is this one piece of platinum iridium metal that like they measured everything off of. So up until like a few years ago, any scale that you use in like a chem lab to like measure out your little grams and stuff, all that crazy stuff, could trace its calibrations back to Lagrange K, which is like crazy to think about. So Lagrange K was like the big boy, right? That was 1 kilogram. And what they would do is they'd take out Lagrange K periodically, and it was sealed in this vacuum under glass container, and they would take it out, and then they would measure it against these things called the witnesses, right? And so they had 6 witnesses, which were essentially exact copies of Lagrange K, but they're like the ones that would get shipped out to like NIST in America, or like they do go all the way like all over the world to like the national laboratories to calibrate their things, and then those would then calibrate the scales that you use in like your college lab and stuff like that. But Lagrange didn't ever travel. It stayed there under glass. And what they would do is they would actually, like, every time they would come out and like measure the witnesses next to Lagrange, they would like polish Lagrange and stuff like that. And they would like take care of it and all that kind of stuff. And they realized that over time, and what kind of spurred the reason for them to change the definition of Lagrange, not actually using Lagrange anymore, is because when they would polish it, little by little, atoms of the platinum iridium alloy would like come off when they were polishing it. So it was no longer a kilogram. It was actually less than the witnesses because they had polished it too much because they were like so obsessed with it. Yeah. So then they don't use it anymore. Okay, bye. That's it.
So now the kilogram is defined by taking the fixed numerical value of Planck's constant h, which we will talk about in chapter 2, when it's expressed in the units of joules seconds, which is equal to a kilogram mass squared per second. We'll get there. And so where the units of meter and second are defined in terms of the speed of light, which again, we'll talk about in chapter 2, and some delta V value, but constants again. So we can see some issues with how these were developed, but they're fun facts. Thank you. So the metric system, which is not used in America, bummer. Jimmy Carter did try when he was president to change the empirical units of measurement, which we use inches, feet, miles. He tried to change it to the metric system. Should have worked a little harder maybe, but we are not in the metric system, but in chemistry we use the metric system. So what's important to note is these prefix multipliers. These you do need to know. What I would say is the most relevant ones for you are from kilo to nano. These ones are important to know simply because we need to be able to convert. 1 kilo is 1,000 equivalents of the base unit. So what this can tell us is 1 kilometer, the base unit being the meter, is 1,000 meters. We can also look at that and say 1 micrometer is 0.000000, oops, excuse me, too many zeros, 1 meters, or 10 to the negative 6 meters. So that's how you would read this. There's the symbol on that side, and here's the actual equivalent of the base unit. You can use scientific notation, or you can use decimal notation. That's fine. Temperature scales. 3 different ways to measure temperature. Again, in America, we usually use Fahrenheit, not so often in chemistry. The reason we stick with more Celsius and Kelvin are the same type of degrees. Just Kelvin does not have any negative values. And so when we look at Kelvin, our smallest absolute zero value is 0, literally 0. That's the lowest temperature we can go. And over on the other side, we see Celsius is negative 273. So there is a conversion factor between Celsius and Kelvin. You add 273 to whatever the Celsius is, and you get the Kelvin. Now what we see is that works with just adding because their degrees are similar. They're weighted the same. 100 degrees of Celsius is 100 degrees of Kelvin. Now the problem is Fahrenheit. Fahrenheit conversion factors we don't often do. We can do it just to get some baseline of what we're talking about. But here's how you would convert between all sorts of different types of temperature. The one I want you to know is adding 273 to Celsius. So whatever your degrees Celsius is, if you add 273.15, you'll get the Kelvin. Notice there's a degree symbol for Celsius and there's not for Kelvin, just because Kelvin is named after its inventor. The Fahrenheit to Celsius you do not need to memorize. Don't memorize that. we won't be using this one a lot. The 1 over 1.8 plus 32 is how we actually get through that 180 divided by 100 idea, 1.8. And then the plus 32 is our baseline for 0. So that's where it comes from. But again, you don't need to memorize those. Okay, when we take our measurements, reliability of measurements, two different ways we can talk about reliability: precision and accuracy. These go hand in hand, but they are not the same. Precision is the agreement or closeness of a series of measurements to each other. So I can go in the lab and measure a specific sample 5 times. If they're all the same to each other or close to each other, they're precise. That doesn't tell me accuracy, right? Accuracy is the agreement or closeness of a measured value to the actual known value. So we can look at both precision and accuracy, but they don't mean the same thing. You can have accuracy but not be precise, right? I could have the Lagrange K, and I could measure it, and it could be 1.01 kilograms, and then the next time I measure it, it could be 0.998 kilograms. Those aren't precise. They're on opposite sides of that actual value, right? They're not close to each other, but they are relatively close to the known value. They're just jumping on either side, plus or minus. Now, that's where we get uncertainty. The uncertainty digit depends on the instrument being used. We won't use this in lecture, and we'll only use this in a little bit in lab 1, since we're all looking at the plus or minus idea. We want to make sure that we know what we're being used to measure. We'll discuss that more specifically when the labs come in. Now, significant figures. These are very important for our lecture and our laboratory, because when we're reporting values, reporting answers, the units are important, that's important, but the actual number that we report can have accuracy and precision involved in it. And so it depends on the precision of the measured values given in a problem. So when we go into the lab, or if we're given numbers in a mathematical practice on our exam, we got to look to precision of those numbers. So conversion factors, which we'll use a lot today, they are exact values. Think about them as an infinite number of sig figs, significant figures. We're not going to look at those as having any sort of lack of precision. They're accurate, very, very exact values. All of these conversion factors we'll see it some way, shape, or form in our life, but also in the lecture and the lab. Here are some rules. The first one is very straightforward. All non-zero values are significant. 1, 2, 3, all the way up to 9, right? All of those values are significant. So example, 536 has 3 significant figures. The 5, the 3, and the 6 are all significant. The rest of our numbers, or the rest of our rules, have to do with 0, because what is 0, right? 0 between non-zero digits are significant. So 6,703 has 4 significant digits, because that 0 is sandwiched in between 2 actual non-zero values. So that one's significant. Leading zeros are placeholders. They are not significant. So all of these right here, not sig figs. The 4 and the 3 are sig figs because of rule number 1. But those leading zeros are just placeholders. They're not significant. Now, trailing zeros, zeros at the end. We've done zeros in the middle, they count. Zeros at the beginning, they don't count. Zeros at the end sometimes count. If the zeros that come after the trailing zeros, those zeros to the far right, don't have a decimal place, yeah, don't have a decimal place. They are not significant. I know it seems silly, but that decimal place gives us an actual point of significance. So if we have zeros to the right, but there is a decimal place in the number, doesn't matter where that decimal place is, but if we have a decimal place, now our zeros are significant. Be very careful with this one. We'll practice that one a lot in lecture and in lab so that we can really get that one under our belt. Okay, precision of laboratory glassware. For the lab, when we think about where to read things, what we see for this type of a graduated cylinder is there's the 4, and it's 4.0. How do I know? Because I have 4.1, 4.2, 4.3. I actually have a marking, or a tick mark is what I like to call it, for these values. And so we know up to the 4.5 right there. Notice where the meniscus is. It's a little bit under 4.6. So I know that the number is between 4.5 and 4.6. So as a good scientist, I can estimate one extra significant figure. So I could say 4.455 or 4.56. That's my one uncertain digit. It's me being able to give my little bit of a 2 cents and my observation in order to say, what's that last value? You can't estimate anymore, only that one digit. So don't put a 0 on the end, don't put a 555. You're not that good. For mathematical operations with significant figures, multiplication and division, the rule is the least precise measurement, so the one with the smallest amount of sig figs, is how many sig figs you report. And for addition and subtraction, we are looking at decimal places. Again, the smallest amount of decimal places is how many decimal places you report. Density is an intensive physical property of matter. Density is defined as mass over volume. An intensive property means that it's independent of the sample size or independent of the amount of sample being measured. These are important: density, color, smell. Some of these might look like observations that are qualitative, but we could also have boiling point. That's a quantitative measurement. Melting point. All of these, it doesn't matter the size of sample. I could have 1 gram of it. I could have 10 grams of it. I could have 100 grams of it. It's all going to be the same intensive physical properties. Now, mass is an extensive property, right? 1 gram is different than 10 grams. Volume is an extensive property. It's dependent on the amount. It could be 1 liter, it could be 10 liters. But notice when we actually take the ratio of mass to volume, the density of a substance is intensive. It's a derived unit, density, and so therefore we can actually see how the physical properties change for samples dependent on what is defining them. Densities of liquids and gases are affected by temperature, but they are not affected by amount of a substance. So the difference between an intensive and an extensive property of matter is very important. Intensive is independent of the sample size. Extensive, it is dependent on the sample size. An extensive property besides mass, volume, we could say surface area. All of those are good extensive properties. We're going to do a lot of dimensional analysis, conversion factors in chemistry. A lot of them in the lab, a lot of them in the lecture. Why? Because we need to convert from one thing to another, whether we start with 5 grams of a reactant and we want to get to how much product, or something as simple as, hey, this is America and I don't know what inches are versus centimeters. Conversion factors such as these will always be given to you. You don't have to memorize them. But what they mean is that you can really put one in the numerator and the denominator, dependent on what you need it for. We'll utilize these conversion factors as exact significant values. So there's an infinite number of sig figs. And we can utilize them how we see fit in a dimensional analysis problem. For instance, when given some sort of a word problem, the best thing to do is to sort out what information you have, specifically identifying the number that you start with, the measurement that you are starting with, and identify any mathematical relationships, i.e. conversion factors such as density or just unit conversion, centimeters to inches. What do you need? What's in your toolbox? Writing those out, highlighting, underlining, those are all great. Then devise a strategy plan. Tell yourself, hey, what am I trying to get to? What units do I need to cancel things out? And that plan will help you then solve the problem. When you pay attention to the actual mathematical operations and significant figures, then canceling out units as we go along. We'll see an example of this in class a few times. And then checking your answer, does it make sense? That's always the last step. So arranging these, if I wanted to say, take 3.0 feet and convert it to centimeters. Now, I need to know how much is 1 foot? Well, I do know 1 foot is 12 inches, and I know that 1 inch is equal to 2.54 centimeters. I would have given that to you on the front of the exam, or it's in your notes or on a table. Now, if I start with 3.0 feet, I need to figure out, how do I convert feet into my unit that I want, right? Well, I know I can take feet into inches, right? So my given unit, feet, is in the numerator. That means in my conversion factor, I want my feet to be in the denominator. Numerator can cancel with denominator. That means inches would need to be in the numerator. Then we slap on the numbers, right? We take that conversion factor and put it into a fraction. Can do the same thing with the next conversion factor. I have inches in my numerator, so inches should go in the denominator. And I have centimeters that I'm desiring to get up at the top. Now double check. This is what it means by verifying. Feet cancels with feet. Inches cancels with inches. I'm left with centimeters in my numerator. Now I can go ahead and do that math. Now what's important is that when you're doing this math, you only are going to report the correct number of significant figures. When we look at our conversion factors, those are infinite values. So here's what my calculator spits out for centimeters. But do I want all those? Am I that accurate to say 91.44? I look at my measured value and I say, well, how many sig figs were there? I have a 3, that's significant, and I have a trailing 0, only significant if I have a decimal place. Well, good, I do. So that 0 is significant. 2 sig figs, 1, 2. The actual answer I report, 91 centimeters. I block it off there and I say, if it's 4 and below, I round down. If it's 5 and above, I round up. Here's another simple example down here if you wish to review. Now, overall, this unit is, or this chapter E is important to go over, and we'll see all of these points as we dive into practice problems together. So if you are reviewing, that's awesome. We'll see all of these throughout our semester together. Thank you so much for joining me.